Well, good afternoon, everybody. Welcome to our distinguished lecture series led by Professor Samini. And we're delighted today to have Professor John Rogers from University of Illinois here to give us a talk. I first met John probably 8-9 years ago on a project that we were both funded from the same sponsor on doing nanomembrane work, and it's pretty safe to say his work was a little more successful than ours was. But it's my pleasure to be here today to introduce him and welcome him to University of Delaware. So let me just tell you a little bit about his remarkable accomplishments. Got his PhD in '95 at MIT, went from there to Bell Labs. I was at Bell Labs for a number of years, joined the faculty at Illinois in 2002, was it, John? Roughly. From there, he's now the Swanlund Chair, professor at the University of Illinois, director of the Seitz Materials Laboratory. There, he has published over 500 papers, has 80 patents with a remarkable number, 50 that are actually in active use or being licensed right now. Long list of fellows, IEEE, APS, MRS, AAAS, member of the National Academy of Engineering, National Academy of Sciences, won the MacArthur Fellowship Award, the Lemelson MIT Prize, the Smithsonian Award for Innovation. I mean, the list goes on and on. And to that end, I am delighted to introduce Professor Rogers today. Thank you very much.
All right, thank you very much for that kind introduction. It's a real pleasure to be here. I've enjoyed tremendously my day and had a chance to talk to a lot of really interesting, high-energy, creative faculty and interact with some students. It's amazing some of the things you guys are doing here. I'll spend the next 45 minutes or so telling you about some of the research that we've been doing at Illinois. I'm a materials scientist, in particular, an electronic materials scientist, but we're interested in devices and electrical engineering and new kinds of systems that have the capacity to integrate with the human body in interesting ways that could have impacts in a broad sense on clinical health care. So if somebody can shift over to my slides, I can actually start my talk at this point. Is this, okay, here we go. Okay, so this is kind of the outline of what I'll talk to you about. I'll start out with a little bit of motivation and perspective of what we're trying to do in this area of sort of novel electronics for integration with the human body, and then step you through two specific types of systems where we've been able to establish some traction. I'll give you some sense of the capabilities and the relevance to clinical healthcare. One is in this area of what we refer to as epidermal electronics. So these are pieces of electronics, semiconductor devices that adopt the physical characteristics of the human skin to allow integration with the skin and use of the skin as a window into underlying physiological processes to develop sort of clinical quality data streams in a wearable type of technology. And I'll describe to you some of the materials and device design ideas that enable that type of system. And then in the last part of the talk, I'll describe something a little bit different. Miniaturized optoelectronic systems that are designed not to mount on the surfaces of organs like the skin or the heart or the brain, but actually penetrate down into their depths in sort of a needle injectable type of format. And I'll describe the use of those kinds of technologies in the implementation of optogenetic techniques for neuroscience research. But broadly speaking, we're thinking about man-made systems, electronics that really begin to look like biology in a mechanical and a material sense. So the vision is to think about taking the kind of functionality that's available in your cell phone, spectacular levels of function and operational capabilities in a very powerful technology platform, and render it or reformulate it in a format that would allow its intimate integration, for example, with the human brain. So the idea is if you want to study neuroscience, you want to treat brain disorders, you're talking about manipulating and studying biology's most sophisticated form of electronics. And our belief is the best way to do that is to figure out how to take man's most sophisticated form of electronics, silicon CMOS electronics, and integrate it, make it look more like biology so it could laminate on the textured surface of the brain to establish an intimate information interface for sensing and actuation. And our thought is that if you could figure out how to do that, you wouldn't stop at the brain. You'd also try to leverage that technology in cardiac science and use it to treat heart disease, because after all, the heart is an electrical system as well. It's an electromechanical system, but if you could develop kinds of electronics that could wrap the entire epicardial surface, maybe you could develop new technologies for low energy defibrillation or spatiotemporal pacing and treatment of various heart disorders. But likewise, if you could do this kind of thing, you could render electronics in a form that could sort of melt directly into the surface of the skin, onto the epidermis, and do that with an eye toward clinical healthcare monitoring and electrical stimulation, for example. So what does that mean in the case of the skin, and what exactly we're talking about? Well, we're talking about electronics, for example, that take on physical forms like kids' temporary transfer tattoos. We think this is a good model to think about because it is one example of a man-made device that does go onto the skin in a way that, from a sensory standpoint, is imperceptible, because the device technology in this case can go onto the skin, and then it can just move naturally with the natural motions of the skin in a way that doesn't physically or from a mass or thermal standpoint load the skin. And so you don't even feel that it's there. And so the question is, what would it take in terms of material science, electrical engineering to build silicon integrated circuits that look like this? And what are we really talking about? We're talking about building circuits that are super thin, so 5 microns in total thickness rather than 1 millimeter, which is kind of the thickness of a commercial IC, set mostly by the thickness of the underlying substrate, very lightweight and aerial mass loading sense of maybe a milligram per centimeter squared, comparable to the epidermis itself. Need to be super low in modulus, so soft in a mechanical sense, because the skin is soft. So we thought 5 kilopascals would be a good target. That's about the modulus of the brain. The modulus of silicon itself, by reference, is 150 gigapascals. So we're talking about an ultra soft circuit technology compared to what's available commercially today. It would obviously need to be able to flex, so just conform to the curved surfaces of the skin, but it would also need to stretch, and that's different. So a sheet of plastic bends, it can flex, but it cannot stretch. So we're talking about something more like latex or balloon type material, thin, bendable, but also stretchable, like a rubber band. And skin stretches up to about 30% strain before it begins to tear, and so you'd like your technology to be able to accommodate that level of deformation. Then, in terms of other kinds of physical properties, you'd want it to be air and water permeable to accommodate transepidermal water loss, but at the same time, you'd want your active circuit elements and your sensors to be waterproofed against contact with biofluids to avoid malfunction or electrical leakage into the adjoining tissues. So that's kind of the set of characteristics you need to think about. And the goal would be not to render a cell phone that you could put on your skin for convenience, but to develop device technologies that, when on the skin, enable kinds of functionality that are essential to that mode of integration. And what we're really talking about are devices that would be intrinsically wearable, like a temporary tattoo, but would have the capability of generating clinically meaningful, actionable data streams that could correlate to clinical gold standards that physicians understand. So we're not talking about activity monitoring with a Fitbit. We're talking about ECG monitoring with a temporary tattoo type electronics to replace this, which works well in a hospital or lab setting, but nobody's going to wear this kind of technology because it's irritating. You've got wires all over the place. These patches are irritating to the skin because they're not modulus matched to the skin. You get a big bulky piece of electronics for data acquisition. So it works well, but it's not really a wearable device. You can't use it in a realistic sense for continuous monitoring. Likewise, if you want to measure hydration state of the skin, what you do today is you use a corneometer. So it's a bulk device, rigid electrodes. You punch it into the skin and you can measure hydration state, but that's also not wearable. It's not really applicable to sensitive regions of the skin. I'll come back to that in a second. So it's the skin of the face, for example. You wouldn't want to punch your face with this kind of thing. So it's limited utility, but that's this gold standard today. If you want to measure blood pressure, or you want to measure pressure wave dynamics associated with blood flow through the vascular system, what's used today is an arterial tonometer. Looks like this. It measures pressure pulse wave variations. That kind of data can be used to assess cardiovascular health and, like I said, hypertension and blood pressure. But again, it's not wearable. It's a bulky piece of technology built around conventional electronics, which from the very earliest days of the industry to the present time have always been constructed on silicon wafer, or more generally semiconductor wafer platforms. And so most of you are probably familiar with these kinds of materials. And you can think of it as sort of a plate of glass, essentially, from a mechanical standpoint. So it's a great, rigid, flat surface for doing construction of integrated circuits. But you drop it on the floor, it shatters into a million pieces. You certainly couldn't bend it and conform it to the brain or the heart. I mean, it's just impossible. So if you think about this problem from the standpoint of electronic material scientists, you might naively conclude, well, I have to throw out silicon, I have to go to a different material, maybe 2D materials, carbon nanotubes, polymer-based semiconductors, what have you. And we have spent a lot of time down that path. And there are a lot of academics who continue to work in that direction. I think at the same time, you'd have to recognize the fact that if you could figure out how to use silicon in a way that would enable these kind of biocompatible physical characteristics, that is certainly what you would want to do, because there's a half-century worth of global R&D that's gone into figuring out how to build reliable, low-cost, robust integrated circuits with silicon. And you'd like, ideally, to be able to leverage that deep base of scientific and engineering knowledge that exists around silicon. So that is the path that has been most productive for us. And I'll just encapsulate it in two simple ideas, and then I'm going to move on to examples of how you leverage these concepts. But if you want to know more details about the base ideas, I'd be happy to answer those questions or discuss them with you after the talk. So here they are, two super simple ideas, but very, very powerful. So the first idea is that any material has a bending stiffness that's defined not only by the intrinsic modulus of the material, but its overall thickness. That's just Newtonian bending mechanics. In fact, the flexural rigidity decreases like the cube of the thickness. So if I go from a silicon wafer, it's a millimeter thick, and I figure out instead how to shave off very, very thin membranes from the surface of that silicon wafer, I can render a form of silicon that's flexible and floppy, as illustrated here by these silicon nanomembranes. So it's about 100 nanometers thick. So much thicker, thinner than the silicon wafer. We figured out how to do this from a material standpoint, and you can do this so you can slice them off at thicknesses that are still sufficient to support all the electronic functionality you want. So make the silicon thin, it becomes flexible. But as I mentioned before, flexibility is not good enough for biointegration. It needs to be able to flex and also stretch. And there's no level of thickness that you can take silicon that will render it into a stretchable form. So you need a second idea added on top of that first one in order to create a stretchable form of single crystal device grade silicon. And the idea is you take these kinds of materials and you form a composite with a soft elastomer that serves as the substrate. So in this case, this is a silicone elastomer substrate, and we've integrated onto its surface an array of very thin silicon nanomembranes, but not in a flat geometry, in a wavy geometry, sort of mechanically buckled, so that the hard, soft, integrated material system that you have here essentially has the elastic properties defined by the underlying rubber substrate, but with the electronic properties defined by the silicon in an overall system that affords a physics that's very similar to that of an accordion bellow. So if I take this thing and I stretch it out, the wave structures in the silicon can change to accommodate that applied strain without fracturing the silicon, which in fact is still a brittle material. So as you stretch it out, the wavelengths of these buckled wavy geometries go up, the amplitudes come down. In a way that affords linear elastic mechanics. Likewise, if you compress this, the amplitudes go up, the wavelengths go down. So that's essentially how it works. Those are the two basic ideas. It turns out you can add on top of those concepts all sorts of engineering elaborations. And so, this was 10 years ago looking at stretchable silicon. Now we can exploit that controlled buckling mechanics and these hard, soft, deterministic composites to do essentially anything that we want with hard materials in terms of the overall physical characteristics of the integrated system. So if you want to do an integrated circuit, for example, you exploit geometries like this, these filamentary serpentine mesh type structures. So here you're exploiting not only out-of-plane buckling, but also in-plane buckling by virtue of the filamentary serpentine design. And so you can make a composite. Hard materials are providing the electronic functionality. There's a soft silicone substrate here. If you pay quantitative attention to the detailed mechanics of how this hard, soft material responds to applied strain, you can optimize the layouts to create an effective material that has stress-strain behavior quantitatively matched to that of skin. So here's a stress-strain curve for skin. It starts to go sort of nonlinear. It starts to rip and rupture, as I mentioned before, at about 30% strain. But it's linear elastic up to about 15% strain. If you look at this composite structure, you measure it experimentally, you see an effective modulus, a slope here about 130 kilopascals. In spite of the fact that you've embedded very hard materials into that platform. Again, 150 gigapascals for silicon. You have an effectively soft material, quantitatively matching up with the finite element modeling results. So if you think about it from an electrical engineering standpoint, now you have to add on top of circuit design, mechanics design to get the full system function that you'd like to have. So this is sort of an ad hoc approach to make a more systematic design strategy. We found that the ideas of fractal mathematics turn out to be very, very, very helpful. So you can take these kind of fractal curves and then essentially tile any area in, at any level of coverage with these active filamentary serpentines in a very systematic way that allows you to do sort of top-down design of the mechanics. So we looked at lots of fundamental fractals such as von Koch curves and piano curves, Hilbert, Visseg. And these things are known, but nobody had looked at the mechanics before. So we've studied this in a quantitative way. We understand the level of stretchability and how it relates to the level of iteration in these different fractal geometries. And this turns out to be a very good way to do things. You put these ideas together, and now you have a systematic design approach for making sort of temporary tattoo-like or epidermal electronics. And here's an example. One of these devices laminated under the forearm of a postdoc who was doing the work. And then we came in just to show the mechanics and poked him with a glass rod. And you can kind of see how the skin deforms. The device forms right along with the skin, not mechanically constraining the motion at all. Again, sort of imperceptible from a sensory standpoint. And furthermore, because the mechanics are so soft, there are very small interface stresses that develop between the device and the skin. So even without robust adhesives or penetrating pins, straps, or glues, these devices can stay adhered to the skin just by van der Waals forces alone. And of course, if you grab them by the edge, you can peel them off, and that's kind of what it looks like. I mean, it's very sort of biological-like or skin-like in its mechanics. It's so soft and floppy, it doesn't even support its own weight, as you can see there. What does it look like at the interface? Here's an example of a colorized image of one of these filamentary fractal-type circuits on a molded replica of the human skin. So your skin at a microscopic level is very topographically challenging in terms of the non-uniformity in the surface profile. But this kind of geometry not only offers the mechanics that you want, but also the conformability that you kind of need to establish, let's say, a low impedance electrical interface for making measurements of underlying biopotential. So this is a very favorable geometry. Here's what it looks like. You begin to put it together and build systems that have measurement capabilities that are of interest. So here we're using the piano fractal geometry, and we can tile that up in layouts that provide equibiaxial stretchability. That is, I can stretch it in any direction. It responds more or less in the same way. And then I can change the configuration of that piano fractal for the interconnect wiring to provide stretchability along the length, but not that much along the width. So you put it together, in this case, designed to not only stretch, but also conform to the complex topology of the auricle. And here we have a recording electrode on the mastoid for measuring brain waves. And we have reference and ground electrodes on the ear. And this is interesting compared to the kind of skull caps that you've probably seen with the conductive gels and the rigid electrodes and bulk wires, in the sense that you can put this on the body, on the ear like this, and it can remain in place for long periods of time, and it can accommodate all sorts of daily activities like showering and washing and exercise and swimming. It's no problem. It's adhered quite well to the skin. It's non-irritating at that interface as well because of the skin-like mechanics. So here's an example of persistent EEG recordings, brainwave recordings for a brain-machine interface that we developed with collaborators at the Beckman Institute, measured over a course of 2 weeks. So this is a grad student involved in the work. Mounted them up on day 1. You can measure day 7. Pretty much the signal quality is unchanged all the way to day 14. Beyond 2 weeks, what happens is you begin to build up cells at the surface of the stratum corneum that would otherwise naturally be exfoliating. It's just a natural process of the skin, but the physical presence of the device frustrates that exfoliation process. So the time scale for that is about 2 weeks, and you begin to build up substantial dead cells at the interface, and now you're sitting on an unstable substrate. That's really the limiting factor. Nothing about the material science or the mechanics or electrical engineering, really limited by the biology itself. But 2 weeks is good enough for lots of things. In this particular case, you do training to develop a brain-machine interface associated with signal processing on this kind of data, and then you can rely on that training without variation over a 2-week period, whereas conventional electrodes, you have to take them off when you put them on. They're not exactly in the same place. You've got to retrain. So the idea of persistent EEG is interesting, but you can measure other kinds of biopotentials as well. If you put these things on the chest, I'll come back to this in a little bit, you can measure ECG. That's electrical activity associated with beating of the heart. And so you can measure cardiovascular health. You can measure beat rate, heart rate variability, and you can also measure respiration rate. As you can see, this overall envelope fluctuates. You can put these things on the leg. You can measure EMG, electromyography. That's electrical activity associated with the contraction of the skeletal muscles. So you can measure things about gait, as you're walking and then standing with this kind of epidermal electronic system. If you compare the signals to those that you capture with a conventional paste-on bulk electrode with a conductive gel, you see the signals are more or less the same. But this is a piece of electronics. That's just an electrode. This has wires, and this doesn't. And I'll come back to the wireless embodiment in a few minutes. So it's biopotentials, brain, heart, and skeletal muscles. You can also measure other things, such as physical deformation. So you can reproduce that kind of arterial tonometry methodology, but in a skin-like format by incorporating lead zirconate titanate, so ferroelectric, piezoelectric materials into the platform. And then you can measure pressure pulse wave dynamics associated with blood flow through near-surface arteries. You can see that here. And if you measure at 2 spatially distinct locations, then you can measure time delays. And those time delays, together with the known spatial separation, can determine pulse wave velocity. And there are FDA correlates between pulse wave velocity and blood pressure. So you have a way to do continuous blood pressure monitoring with this kind of platform. You can do other things as well. You can measure temperature to extremely high levels of precision in devices that don't perturb the natural temperature of the skin. So you design these things to have thermal mass that's a very tiny fraction of the epidermis, and it's also permeable to sweat. So it doesn't load or alter the temperature of the skin, but at the same time it provides millikelvin resolution and precision in the temperature measurement, and you can do that in a mapping configuration. So we worked with experts in skin thermography at the NIH, and they have $250,000 IR cameras that allow them to track subtle variations in temperature. We can quantitatively compare that data to those that we capture with this epidermal electronics, essentially exactly the same. But we don't have the motion artifacts, and it's in a wearable format as opposed to something that's only relevant in a laboratory setting. So these curves are actually offset for the purposes of comparison. But you can see these natural oscillations, these very fine temperature variations. That's just associated with natural patterns of vasoconstriction and dilation. And so the amplitudes and the frequencies tell you something about cardiovascular health. In this case, the patient was asked to start to do mental math, so subtraction and division in their head. That causes a little bit of perspiration. Evaporative cooling leads to rapid decrease in the temperature. You say something about cognitive state there, physical stimulus as well. But what's additionally interesting about these platforms is you can do temperature sensing, but you can also do precision delivery of thermal power to the skin. So you can heat the skin by very minute amounts, and then you can measure simultaneously how that heat moves laterally through the skin and down into its depth. And so here's an IR camera showing one of these devices with 4 pixels lit up, and these sensors can then be used to track thermal diffusion. And it turns out then you can determine the thermal conductivity, the thermal diffusivity, and the heat capacity of the skin with these same platforms. And that's interesting because it turns out that the thermal conductivity quantitatively correlates in a linear way to the moisture level or the hydration state. So now you can throw out your corneometer and you can use this type of patch to measure hydration state. And you can see that correlation here. So this is thermal conductivity measured from the time dynamics of how the skin heats up when thermal power is delivered to its surface and how it cools down when that power source is eliminated. So hydration. You can also determine blood flow. So if you take one of these devices and you reconfigure it so you have a radial array of precision temperature sensors with a thermal actuator in the middle, and you align this thing with an underlying blood vessel, such as an artery, then the resulting distribution of temperature induced by activation of that thermal actuator is anisotropic, because it has a directionality associated with the direction and the volumetric rate of blood flow. And so you can see that in this temperature map, it's skewed in the direction of blood flow, and with quantitative models of the 3D thermal diffusion physics, you can extract from that degree of anisotropy the volumetric flow rate of blood through that vessel. And it turns out that you can correlate that measurement to the clinical gold standard, which in this case happens to be a laser Doppler-based technique, super sensitive to vibration, motion artifacts, certainly not wearable, but that is the gold standard. And so what we did is we mounted one of the devices on the forearm, and then we could occlude the radial artery to shut off blood flow, and then we can measure the dynamics of how that occlusion leads to rapid decrease of blood flow measured by the laser technique. And then when you release the occlusion, the blood flow rate overshoots the steady state value and then decays back down. And you can measure that thermally with this epidermal patch, and you can see it here. The occlusion causes a noticeable change in the change in temperature due to the difference in thermal physics associated with the absence of flow. And then you see the overshoot, and it comes back in this way. And you can do all of this sort of in real time with data acquisition systems. And this is showing a measured profile of the flow associated with occlusion there, and then release, and you see it overshoot and then come back to steady state values. So you can do lots of things. That's macrovascular flow. You can also measure microvascular flow, where you're measuring the aggregate effects of flow through lots of blood capillaries. And the best way to see that is in the context of this dermatographic urticaria. Basically, you take your forearm, you slap it, it creates a red region at the point of trauma. You can see the temperature goes up, which sort of makes sense because you have enhanced blood flow near the surface of the skin. But what's even more interesting is you see the effects of increased thermal conductivity associated with the increased blood flow. So the steady state value of the temperature increase for given thermal power input decreases substantially before the trauma and after, and that's due entirely to the increased blood flow. So you can measure wound healing, you measure infection, other kinds of things associated with increases in microvascular flow near the surface of the skin. So these tools are providing sort of interesting measurement capabilities, ideally for a wearable type geometry, but they have utility in the clinic as a replacement for traditional tools. And we've done many human clinical studies with various collaborators at many medical schools. This is one where we're measuring actually the stiffness of the skin associated with cancerous sites. And we offer the opportunity to engage in these studies to 33 visitors to a dermatology clinic at University of Arizona. And 32 of those folks agreed to volunteer to participate in the study, which is a remarkable thing because you think about the age group represented by most of these visitors to the clinic. It's not people who are exactly the most open to new technologies, but I think compared to things they typically are encountering in a clinic, syringes and hammers and forceps and this kind of thing, this skin-like technology is not nearly as daunting or concerning. So I think patient acceptance is ultimately going to be very, very important for distribution of these kinds of technologies, and this is at least a data point that they're very willing to do it, even on very sensitive regions of the skin, as illustrated here. So for those kinds of applications, you need sort of data acquisition systems. There's wires coming out of the device for measurement. You just measure the modulus of the contact of the skin. It's maybe 30 seconds, then you're done. We've done a lot of work with L'Oreal. They're very interested in skin health because that affects skin beauty and appearance and so on. They're very interested in hydration state, microvascular flows, determining the redness of the appearance of the skin. And so we've done a lot of studies with them on facial regions of the skin where you can't really use a corneometer in any kind of realistic sense. And so in that case, they funded us to develop a complete sort of graphical user interface and a complete box of electronics for doing the measurement. The actual skin interface part of the system is down here. And so we've done probably 100 studies on human patients in this way. And this is kind of what the setups look like. There's a lot of hardware, but it's fine for these kind of lab-based studies. But ultimately, I think the real value in these technologies is getting rid of the wires, getting rid of the power sources, making them fully functional and freestanding in this temporary tattoo-like format. And so that's been the focus of a lot of our work over the last couple of years, and let me just describe to you what's possible. So now we're talking about designing RF systems, to get rid of the wires, to do RF transmission. And it means you have to think about RF circuit design and antenna design in the context of a platform that's stretchable. And it's on a time dynamic substrate, the skin, for example. And so we focus primarily on HF region of the RF spectrum for data communication and power transfer. And so this is a very simple example of a NFC chip and a magnetic loop antenna for inductive coupling to NFC hardware in a cell phone, for example. And if you're paying attention to the geometries and the mechanics and the materials, you can render these things in skin-like geometries as illustrated here, but with the additional design criteria that you got to get the mechanics right. It's got to be soft and skin-like, but even on full extension, you can't tolerate large changes in the center frequency. And so you really have to do the mechanics and then the full electromagnetics on the mechanically deformed antenna to understand how it's going to behave. And in this particular case, it's operating at about 13 megahertz. And throughout the range of strains relevant to skin, 0 to 30%, there's almost no variation in frequencies. This is experimental results and simulation results where we're combining abacus calculations of the mechanics with HFSS calculations of the electromagnetics. So adding that additional feature to this multi-physics problem. But you put all that together and you make systems, again, like temporary tattoos, but in this case, with the ability to store and read out data. And there is interest in this kind of thing in authentication and payments and other kinds of password storage. And this is just a short movie showing you how that works. This is one of these devices. And the movie will show its operation under an extreme state of deformation, was sort of the design goal. So this is a system, you squeeze the skin, you can see the device sort of crinkle up like that, but it's still able to communicate to the phone. In this particular case, it just has a simple message that, I am a skin-mounted RFID tag, and so that works. One of the first people I showed that movie to, they said, "Oh, cool, that's pretty neat. You can like squeeze the data out of your device," but that was not the point. It was just show it's functional when pinched in that way. Now that's a pretty simple example. I'll come back to that in a second, but it turns out that platform is very, very powerful because of the sophistication, rapidly increasing sophistication that's available in NFC technology. Very small chips, maybe 0.5 millimeter on the side, you can grind them down 25 microns, just like a little poppy seed essentially in a platform that includes sensors as inputs, but the latest TI NFC chip includes a CPU, MSP430, has memory module, 4 high-speed ADD channels, power regulator, and then an NFC interface that provides, through one of those kind of magnetic loop antennas, coupling to an external reader where the range can be up to about 1 meter for power transfer to activate the device, capture the sensor inputs, and then to wirelessly transmit the data back out for capture and analysis. And we think that's a very powerful kind of approach because it doesn't require a battery. That's the key. So here's a device designed to measure ECG. So it has these fractal-based electrodes. You can see them there. It has this serpentine magnetic loop antenna here. And there's the TI NFC chip. This is an op-amp. So you put this on the chest. You can measure ECG wirelessly. That's the kind of trace you see. If you put bulk electrodes, paste on with gels here and here, with wires to $50,000 box of electronics, the clinical gold standard, this is the data trace you can capture. And so very good quantitative agreement here. The total cost of this device is about $1.50. The chips are very, very cheap. So here's what it looks like. This was a near-field reader. I'll just show you how this works, and then I'll show you with a long-range reader system. So there's the patch on one of the graduate students. This is the sort of wireless power delivery and data acquisition with a range of a few centimeters. And this is real-time ECG coming out here. These red triangles here, that corresponds to real-time peak detection that's happening at the MSP430, so we're transmitting that data as well. You can immediately get heart rate variability, and respiration rate from that kind of data, as well as detailed cardiovascular health analysis associated with the full waveform. So that's how it works, but these things can operate remotely, completely remotely. So here's one of these devices, no battery. We have about a 1 meter distance between the large loop antenna that's transmitting power. It's lighting up the MSP430 in this case. The ADD channels are pulling out the signals measured from these ECG electrodes, and then it's doing real-time peak detection, signal processing on board, and lighting up that LED at a time that's coincidence with each beat cycle in the heart. So you can just look at this thing and determine heart rate. Again, no batteries, and so the device can be very, very thin and skin-like in its construction. You can also do other things like light up LEDs. You can use photodetectors, full spectroscopic characterization capabilities of the skin for oximetry, PPG, other kinds of things. What do you use this for? I think there are lots of things that you can imagine. This is a vision that we've had for a half decade by now, but I think we're finally at the point we can realize this. So if you go to a neonatal intensive care unit and you look at what's happening with premature babies, this is what you'll see. So these are very fragile infants, and you have to monitor all of their vital signs continuously. At the same time, their skin is very fragile, and their muscles are not well developed. So it's a sort of horrific situation. You got all this hardware, you got tapes and straps and gels. Some cases that leaves permanent scarring on the skin. So that's a problem. It would certainly constrain the natural motions of the infant. That's also a problem. And it also frustrates the mother-child interaction, because every time the mother needs to sort of pick up the baby and interact with it, you got to take off all this crap, and you have to put it back on again. So the idea is if you could use these electrical engineering ideas, chuck all that stuff and replace it with a few of these patches, that would be something probably worth working on. So this is Photoshop. So at this stage, this was 3-4 years ago, we didn't have these devices, so this is very much a vision. But we're now at the point we could actually do it. So we have devices in the neonatal intensive care unit at Lurie Children's Hospital. This was the first baby that we got these devices on. And for me, this is one of the more satisfying pictures of a research outcome from the group in the last decade. Satisfying for two reasons. One is we finally figured out how to do this. The reed antennas in the base of the isolate. And so you're always within a meter here. But the other thing that's satisfying is not only is this an outcome of the group efforts, but this is as well. This is a baby, a couple of postdocs in the group produced that. So that was kind of cool as well. I didn't see that one coming, actually. I saw the technology coming long before the baby, but they're very, very fortunate. So where is this in a commercialization sense? It's being launched in sort of basic geometry by L'Oreal for measuring UV dosimetry. So this is the same kind of architecture, NFC-enabled electronics, but in this case with UV-sensitive dyes printed on top. And so L'Oreal has a large market presence in sunscreen, and they will be giving away these devices with each bottle of sunscreen. They'll produce 1 million devices this year and 3 to 5 million next year. And so this is cool because it means we're all the way to commercialization, at least at the beginning stage. And the other thing that's cool about L'Oreal is they understand style and aesthetics and stuff that I have no idea about. So this is the package. About half the device cost is actually the package. The device itself is only about 50 cents. The package is about equal to that. There's all kinds of advanced materials here. It's a very advanced manufacturing flow. It took a long time to figure this out because you have super thin flex PCB technology combined with skin bandage technology, and the whole thing looks like that. Spools out in a very fancy way like this. And I'll show you a real image of one of these devices in a second. So they go onto the skin for 3-4 days, and it provides the NFC interface to the phone. The phone camera grabs an image and then automatically does color analysis and renders quantitatively accurate data on UV dosimetry. And it's through the sunscreen. So it's a skin-like patch. You just apply the sunscreen right on top, and then you're getting sort of exposure dose from that. So that's the end of what I wanted to tell you about skin-like electronics. We just make the comment that the same ideas in electrical engineering, mechanics design, materials science apply to all kinds of organs of the human body, not just the skin. And I'd mentioned at the outset that we're interested in brain. So we've done a lot of work in brain interfaces for diagnosing brain disorders, primarily epilepsy, with the University of Pennsylvania group. And here's the epicardial electronics I referred to in cartoon form early on in the talk. We do all kinds of semiconductor devices, even LEDs. I'll come back to that in a second. And so all this is great, but if you think about it, you're really only interfacing with the surface of these organs, and there's a lot going on down into the depths of the tissue. And so how do you interact with things into the depth, and what might you be able to do with even more advanced capabilities than this, let's say in the context of the brain? And why would you even want to do that? And I think the reason why is that there is a general consensus, and I'm a believer in this as well, is that a lot of times advances in science are launched by new tool development. And this is Freeman Dyson, but Tom Insel at NIH believes this as well. In particular, in the case of brain science, new tools will enable new fundamental understanding. And that's great because, like, I'm a tool guy. That's what I do. So that we kind of lucked out on that. So let me give you one example of something that we've been working on in the context of a new methodology that's becoming absolutely ubiquitous in neuroscience. So about 6-7 years ago, folks began to develop techniques for genetically modifying specific targeted neural circuits in the brain in such a way that you can either excite them or inhibit them in terms of their electrical activity by exposing them to light. And this is referred to as optogenetics, and it's a giant leap forward compared to the kind of electrical interfaces that have been used in the past, which are totally nonspecific and compromised by all kinds of parasitics, thermal loads, and other things that make it very difficult to use in a targeted way. So these methods in optogenetics are essentially completely replacing electrical approaches in doing neuroscience research. And that is a huge advance, and the neuroscientists who develop these kinds of techniques are absolute geniuses in terms of what they've been able to do. But lucky for us, they're absolutely horrid optoelectronic engineers. So here's what they do to inject the light in. Basically like a fiber optic cable, essentially unmodified, and just plunge it down into the brain. That's it. And then you take a little bit of super glue, you cap it off, you got a ferrule here, and then you attach the other end to a laser. That's it. And so now you can deliver light, sure, into targeted regions of the brain. You can use these kinds of things, but the whole point is to understand the behavioral influences of excitation or inhibition. So you're trying to watch the behaviors of an animal as you launch light into its brain, but you have them tethered up, this bulky hardware, which is sort of constraining the natural behaviors that you want to study. It also prevents social interactions from being studied as well, because if you introduce this mouse with this mouse, they immediately become tangled up, and then this one starts chewing on that guy's, and that one's chewing on that guy's. It's impossible. You also cannot allow them to run around in a natural environment that has sort of 3D topology with it, and running wheels and other kinds of things. It's just impossible because you've got this hardwired connection. So we got interested in this because, as in the case of silicon, we figured out how to make all sorts of very, very thin but otherwise high-performance semiconductor devices, not just transistors and sensors and stuff, but LEDs as well. So I won't get into the details, but we know how now to make super tiny indium gallium nitride and other kinds of compound semiconductor LEDs. In this case, we do an undercut etching process, not too dissimilar from what we do with silicon, but in this case, we can pop off the surface of a wafer super thin and lithographically defined high-performance LEDs, and we have ways to pluck them off and move them around. I won't get into the details of that, but just make the comment that you can create now LEDs that are thousands of times smaller than anything that's been previously possible to my knowledge. In fact, you can make them so small they're comparable to the size of an individual neuron in the brain. So this is a conventional size LED. We can do big ones. We can also do super small ones. And even far smaller than this is 25 by 25 microns. That's limited by what we can do in our lab, but you can go even smaller. One of the key things is thin. So you don't have to do wire bonding. You can just print these down and then treat them like a thin film in terms of doing lithographically defined interconnects. You can put them on plastic, you can bend them, you can make arrays of them. We have companies set up to try to do displays. So we have joint development efforts with very large companies in the semiconductor and consumer device space. And so this is a brand new display technology where we're using inorganic LEDs instead of organic LEDs. But they're super small, 3 by 3 microns, there's about 100,000 of them. And then we do this in a printing type process. So far higher in brightness and speed, lower in power consumption, and better in long-term longevity than anything that's possible with an organic. So that's interesting. In the context of biology, what it means is you can create cellular scale LEDs, which by comparison to the fiber optics that people in optogenetics have been using in the past are just ultra miniaturized. There's one of the LEDs sitting on a fiber optic cable, sitting in a cell culture. You can see the size there. So we can print these things down onto plastic substrates, similar to the ones that we're using for our epidermal electronics. Here's an array of 4. And so they're super thin. You can put them on super thin plastic, so thin that it's easy to sort of stack up other kinds of devices. You make a multifunctional device, not just with light emitting capabilities, but light detection capabilities. You can measure or stimulate electrically if you want. You can measure temperature. That turns out to be super important. I'll come back to that in a second. And even after you've stacked up all of these layers, you still end up with a platform that's a small fraction of the diameter of the optical fiber in terms of total thickness, only maybe 25 microns or so. In fact, so thin that it doesn't even offer the kind of mechanical rigidity that you need to penetrate into the brain. You try to penetrate into the brain, it just buckles. So what we have to do is we use a bioresorbable adhesive to mount this thing on a thicker injection microneedle to provide the stiffness. And then once the thing is inserted in, we pull the injection needle out, leaving the optoelectronics behind in the brain. So here's one of these devices threaded through the eye of a needle. and then sort of wrapped around the shaft so you can get a sense of the size scale. Very, very thin, very tiny LEDs, very, very flexible and biocompatible, again, from a mechanics standpoint. Here's what it looks like going into the brain of a mouse. So you open up the skull. This is the same stereotactic apparatus that people use for the fiber optics, but now you're delivering the light source directly into the brain rather than just a waveguide. So you come down. Here we add some artificial cerebrospinal fluid to accelerate the dissolution of the bioresorbable adhesive so we can pull out that injection microneedle, leaving the optoelectronics now buried down into the brain, with wires coming out that allow us to do the power and the control, and I'll come back to that in a second. But you may be wondering, okay, it's fine, now you have an LED into the brain, aren't you just going to burn up the brain? I mean, you think about an LED flashlight or a headlight, you got massive metal heat sinks trying to manage thermal flow, and the brain is tough because it starts to degrade permanently for increases of temperature more than about 1 to 2 degrees Celsius, that's it. So the thermal budget is very, very challenging, but it turns out that this works, and we did a lot of studies on the thermal physics before getting these things into animals to make sure that this was going to be feasible. And it works for 3 reasons. One is the LEDs are super small, so the surface area to volume ratios are very high, so the passive rate of thermal diffusion is very high, so that's good. Number 2 is for optogenetic stimulation, you run at a very low duty cycle. So millisecond pulses at few hertz in terms of repetition rate. So the total amount of time that the LED is on is very, very short. And then the third thing is that there's natural blood flow in the brain, and that acts as a liquid heat sink. I mean, based on the same kind of physics I was mentioning to you before in the context of blood flow measurement through the skin. So you put all those 3 things together, and you can measure and model then the thermal dynamics of LEDs in the brain. And this is what's showing then. This is change in temperature measured in situ using that temperature gauge, very similar to the ones that I described for use on the skin, so super high precision. And we can measure the steady state increase in temperature at different repetition rates with fixed pulse duration. So we're changing the total thermal load. And even at 20 hertz, we end up with peak temperature increases that are only about 1/10 of a degree, so 10 times lower than the damage threshold, and in quantitative agreement with thermal models of the heat flow. So this is good and sort of lucked out for those 3 reasons that I just mentioned to you. So you can get LEDs in the brain without a problem. So how do you do the control and the power delivery? Well, it's the same RF kind of ideas, but in this case operating at a higher frequency in this particular case. So we have these filamentary serpentine designs in the antennas, embedded in a soft elastomer, so the whole thing is conformal, and then we have the injectable LED part here. So this thing is small enough that it can be mounted completely subdermally. So the whole system mounts under the skin, the power harvesting and control electronics here, and then the LEDs down into the brain. So mice with these devices look exactly like mice without them. There's essentially no difference there. But if you think about the electromagnetics and the electrical engineering of the antenna, it comes back to this interesting problem I mentioned to you before in the context of the skin. Here, these are operating at 2.3 gigahertz. So there is some shift in the frequency. You take this antenna and you stretch it this way, it deforms mechanically like that, and the resonance shifts as you might expect. But we choose the quality factor so we have enough bandwidth here that it doesn't kill the operation of the antenna and the ability to receive power remotely from a patch antenna. So we just design the system in that way. And so these things can be used in the brain, but you can also do optogenetic stimulation of the sciatic nerve, the spinal cord. You can get these things in. Their survivability is very good. They can last 9, 12 months in an animal. You can see the fur in this case is completely regrown. So we're controlling the LEDs, delivering the power in completely wireless fashion. So here's an example of a mouse with an LED in its brain, and we have a patch antenna at the base of the cage. And so I'll roll this movie, you get a sense of this. So this is a very special mouse, as you can see. So we're lighting him up, and I think he has no idea he has an LED in his brain, but in fact he does. So you can use that then to do optogenetics experiments. I won't go into the details of this. This is more sort of in the realm of neuroscience, but here's a canonical experiment whereby you do the genetic modification such that exposure to light activates neurons that produce dopamine, and the dopamine creates a pleasure response in the animal. And so you can train the animals to do all sorts of things without any physical reward, just by lighting up the LEDs at appropriate times. So here's an example. The mouse is running around in this Y maze, and the mice tend to like the end points of these, this Y-type structure. But if you consistently light up the LED whenever the mouse is in this part of its environment, it grows to develop a strong affinity for that part of its world, so that even if you're not lighting up the LED, that's the only place the mouse wants to stay. So this is a very clear example of optogenetics operating in this fashion. So we've done a lot of things with that kind of technology, selected sets of collaborators. The problem is those devices that I just described to you are hand-built. So we cannot support the needs of the broader community, but a lot of people have been interested in inquiring with us about the availability of the technology. So for the last year, we spent a lot of time figuring out how to render those basic concepts in manufacturable form. And that's what I'm showing you here. So we're back to this HF magnetic inductive approach because it's just more robust for neuroscientists who have no interest in futzing around with RF equipment. So we go back to HF regime, and we have this serpentine type geometry, so we can fabricate the whole thing in a planar state. We have the injection needle, a tab back here. You can pull this thing out of the plane, and then we have an indicator LED. It's a red LED that sits subdermally, and the blue goes down into the brain. So this is what one of these devices looks like, operated in wireless fashion. You can get freedom of motion here, so you can rotate this thing in, inject it down into the brain, and then this loop antenna sits subdermally along with the rectifier elements over here. So here's the operation of one of these devices where we have a loop antenna down here, and it's not over here. So we're doing the same kind of place preference optogenetic studies. So whenever and these aren't trained animals yet, but whenever they come over here, the LEDs light up. They get the dopamine going over here, and whenever they go over here, the LEDs are off. And you can do lots of devices, and the animals seem to be perfectly happy with the fact they have LEDs in their brain. There's no effect on their social interactions or any kind of their motion or activity level. So we've launched this technology. It's not a big business, but we sort of feel obligated to provide it to the community. So we sold the first 10 systems to a selected set of beta testers. April 4th and 5th did the training. We had live demos at the Society for Neuroscience meeting in October, so it's very exciting. So we're putting this together and trying to make it more broadly useful. So instead of just generating hero papers, we're trying to take it to the next level and get it out there, essentially let people use it. So that's all I had to say. I think I'm more or less on time here. So let me just conclude by making a comment by some simple ideas in mechanics and materials, electrical engineering. You can really render high quality electronics in biocompatible soft forms. And there are consequences in these kind of next generation wearables, epidermal electronics, and in these injectable systems in optoelectronics and optogenetics. And I think the broader commentary is that new science can lead to new technologies with potential for widespread use, and I think that's the ultimate goal and what we're attempting to do. But it's highly multidisciplinary, and we rely very heavily on collaborators, both in engineering science. Yonggang Huang does all the mechanics, modeling, Placid Ferrer, the manufacturing systems, Ralph News on chemistry, Ruz Ghaffari at MC10 helps with a commercial translation. But everything that we do is tries to address known problems or limitations, unmet needs in clinical medicine and neuroscience. So Mike Brukas on optogenetics, Rob Giroux on pain therapy, Brian Litt at UPenn and epilepsy, and Amy Poller on this neonatal intensive care unit. She's head of dermatology at Northwestern University. So those folks are important, but the most important people are actually the people who do the work. So I just get to talk about it. It's really a phenomenal collection of postdocs and grad students and undergrads as well who actually do the stuff and come up with some of the best ideas, quite frankly. This is a picture from a recent group party. So it's a large collection of folks. This makes the group look a little bit bigger than it really is because that is not a postdoc and that is not a graduate student, but it's sort of more of a family affair. So with that, I'd be happy to answer questions if you have any. Thank you. Yeah, so the light activates neurons that produce dopamine, and then the effect of dopamine is an overall pleasure response. So the light itself is not releasing the dopamine, it's activating neurons that produce dopamine. Yeah. These are experiments that have been done in the past with fiber optics, so we wanted to do with the injectable LEDs just to make sure everything's working. Yeah.
That's interesting with regards to dopamine production with regards to this technology you have, because it sounds like this could be used in cases where people are not producing enough dopamine, say like cases for like drug addiction or like say if someone's suffering from depression. I just wondered, what are your thoughts on that?
Yeah, I mean, I think that's a really interesting direction to think about. So there are various kinds of electrotherapies that are already used to treat brain disorders. Parkinson's is one of the most prominent ones. Deep brain stimulators have amazing efficacy in that kind of case to eliminate essential tremor. For optogenetics, it does require a genetic modification of brain cells, right? And so you can imagine there's an approval process that's required, to ever use that on humans. And I think there are folks in the community who are optimistic that that will eventually happen, but that would have to happen before we'd be able to leverage our devices for a human condition. But I think it's an interesting direction to think about. The immediate opportunity is to facilitate neuroscience research on animal models to get a better understanding of how the brain works and how brain disorders relate to brain function. Got somebody up here. Yeah. Yeah, right. Well, it's a good question. So the question is, the devices that I've shown are being powered by RF, either in that HF range or the UHF range. There are pros and cons about those two frequency ranges in terms of operability and overall distance and sensitivity to dielectric properties and metal and so on. And so there's some practical considerations there. But conceptually, they're both using the same idea, sort of wireless transmission of power into the device. It has the advantage that you don't need a battery, as batteries are not scaling in the same way that electronics are. So it's hard to make a battery skin-like. I mean, you can kind of do that, but not at the level that I've suggested around the sensors and so on. But with RF, you just need an antenna. So you can, in fact, make epidermal antennas. So that's why we like it. That's why we've used the approach. The other thing is you can deliver substantial amounts of power. 50 milliwatts is no problem. And so if you think about, as you're suggesting, using natural body processes to generate the power, to get 50 milliwatts is pretty tough. So I think it's still useful to think about thermal gradients from the skin to the ambient and thermoelectric devices that you could wear in the skin. The problem is you need thermal gradients in order to capture the power. So you need something like delta T, so that sort of drives you to thick devices so you can capture the full difference in temperature. So it's difficult to see how that would work. I still think it's interesting, but kind of research topic. You can imagine epidermal solar cells to capture energy from ambient lighting. You can certainly do that, no problem. Getting to 50 milliwatts is probably not in the cards with the kind of PV cells that exist today. The other thing is motion, body motion. So you can use the kinds of piezoelectric sensors that we were using to do arterial tonometry to capture power. That's reasonable. We've done some devices that go on the heart, belong in the diaphragm, because they're constantly in motion. And you can capture power in that way. But it's kind of at the microwatt level. It's not 50 milliwatts. But that's interesting to think about. There are other groups that have proposed fuel cells, glucose, for example, just harvest that in the body and capture power from that. We haven't done any work. I'm not sure what the power budget would be, what would be realistic in that context. But the answer to your question is power is a big challenge. We like RF because it's addressing the needs of the applications that we have in mind. But I think there are a lot of research opportunities around how do you create power, harvest power from the ambient or for natural body processes. It's a very good question. I think there's some opportunities for good ideas. Let's put it that way in that space. Yeah.
You said you're getting 6 to 9 months survivability on these implants. Mm-hmm. What's the ultimate failure mechanism and failure mode?
Penetration of biofluid. So that is a major challenge, I would say, for chronic implants. You want to think about pacemakers, something like that, talking about the life of the patient. And you have to have a thin, flexible piece of electronics operating in warm salt water for that type of time frame. That is very, very hard. I think it's a great challenge for material science, how to develop barrier coatings that are robust in that context, and that's something we've been working very hard on for a long time. For the devices that are operating in the mice, 9 months is way longer than any of the neuroscientists need them to work anyway, so we kind of stopped focusing on that system. We have other efforts in encapsulation layers, but it's penetration of biofluids through, it's a silicone elastomer to give it the overall mechanics, and then we have layer parylene on top of the metal traces, which themselves are sandwiched in polyimide. So it's really 3 layers of polymer that the water has to go through, but there's no polymer that's hermetic. So you're just slowing down the kinetics. You're not preventing the penetration, you're just delaying it. And so 9 months is kind of where we are for that reason. Yeah.
I was just curious if you looked at the measuring blood glucose. You're measuring blood pressure, but blood glucose is the other one that people want to measure.
Yeah, I think that's a great question. We have not been active in that area, not because I don't think it's a compelling problem to work on, but it's an old problem where lots and lots of people have spent lots of time. And so if I thought I had a new idea, a new perspective on that, we'd jump in and do something. But I think there are so many groups that are far ahead of where we are. Maybe we could use our platforms in the context with somebody else's glucose sensor and do something there. But I think there's a huge need for that, obviously, but we haven't focused on it. So it's a good question. I just don't have anything to share in terms of different approach compared to what's out there already.